So very soon I'll talk about results using the re-ranking approach, using the kind of features I just described. But first I want to talk about a first method for parameter estimation, namely a method for finding these V parameters. And this is a variant of the Perceptron algorithm. We'll see that it's a very simple algorithm, but empirically it turns out to work really quite well on a wide range of natural language processing problems. So here is the algorithm. So we're going to assume that as input we have some training set, some set of examples, xi, yi, for I equals 1 to n. And we have these functions gen and f, which I just described. So gen enumerates the candidates for an input, f defines a feature vector mapping, and we'll assume these two components are fixed. The task is going to be to learn our parameters v using these training examples as information. So we initialize all of our parameters v to be 0. So we set v equals the vector of all zeros. That's the starting state. And then I'll define capital F for any input x in exactly the same way as before. So we enumerate all possible structures y in the set gen of x. For each structure we can calculate a feature vector, f of x and y, and we take the inner product with v to calculate the score for that structure, and we take the highest scoring member of gen as the final output of this model. Initially, when all these parameters are 0, all of these structures are going to have score 0, and so this is going to be a tie. Let's just assume in that case we have some arbitrary way of choosing between the tied members in the argmax. That's a minor detail. The other input to the algorithm is t, capital T, which is the number of iterations the algorithm is run for. And one nice thing about the Perceptron is that t can often be quite small, maybe 5 or 10 or 20. Okay, so the algorithm proceeds as follows. So I make big T passes over the data. That's what this loop here does. And at each loop over the data, I pass over the examples from I equals 1 to n. So I go through a single training example at a time. For each training example, I do two things. Firstly, I calculate the current output from the model. So z sub I is going to be the output of f on xi. It's going to be the highest scoring structure under my current parameters. Now, if zi is equal to yi, that means that I've correctly recovered the correct structure on this particular example. And in that case, I do nothing to the parameters. I leave the parameters v unchanged. The idea here is that if it's not broken, don't try to fix it. We've not made a mistake on this example, so let's leave the parameters unchanged. If, however, we have zi not equal to yi, then the structure we've produced is somehow different from the target structure yi, and in that case I make an update to the parameters v. The updates look extremely simple. So we simply take v, the new value for v is the old value for v, and we add in the feature vector for xi, yi, and we subtract the feature vector for xi and zi. So remember, all of these vectors are in some d-dimensional space. So the parameter vectors are d-dimensional, and the feature vectors are also d-dimensional. And so there's no clash here. These computations make sense. I'm adding and subtracting d-dimensional vectors. Intuitively, what is going on here is that any features which are seen in the true candidate structure have their parameter value increased, whereas any features seen in the incorrectly proposed structure have their feature values, or sorry, their parameter values decreased. So this is kind of a reinforcing step which pushes up the parameter values for things seen in the truth and pushes down the parameter values for features seen in ZI, which was the incorrectly produced structure. So that is the perceptron algorithm. The things to stress are that the inputs to the algorithm are a set of training examples and definitions for gen and f, and also a specification of t, the number of passes over the training set, and the output is a set of parameters v. As I hope you'll see, it's a very simple algorithm which just relies on decoding at each step, finding the highest scoring structure under the current model, and then if we make a mistake, making a very simple update to these parameters v. There's actually a quite rich theory underlying the perceptron and justifying it, both in an algorithmic sense, defining when it converges, and also in a statistical sense, describing why it can generalize well to new test examples, or at least specifying conditions under which it is guaranteed to generalize well to new test examples. We'll try to post some pointers to papers on those topics on the course. I'm not going to go into detail about the theory underlying the perceptron.